This means that I am remotely controlling the microscope that is currently standing in your lab. And with the help of Robert, we are here controlling samples and the microscope itself, but I will try mostly to control everything on my own. And then to use this kind of explanations to train you in how to use the LSX software. Before we start, what we need to do is that we clarify what is the level of experience that everyone has, okay? Because there might be times where I over-explain stuff and you don't need to know this anymore, and then please just interrupt me, or the other way around, that I'm just go over stuff super fast and actually you didn't get what I wanted to say. Okay, so today it's a training, it's for you, so every one of you should be able to afterwards operate the system. Okay. Good. Are there any further questions? Because otherwise I would say I start in a way that I'm briefly explaining what are the different areas in the software user interface that you can control, and then how we set up experiments. This would be basically it. If anyone has a question, there should be also the possibility in the app to raise your hand, and then maybe Patrick can interrupt me and say there's a question, obviously in the chat, or somebody has to unmute his or herself, and then you can ask a specific question. Good. Then if everything is clear, I will start with explaining the software. So you can see in my cursor, the FK is actually my, those are my initials. And I can also pinpoint here to certain buttons and then make maybe a visual highlight for you to see where's the person talking about. Okay, so this is the standard user interface that you see once you start the LSX software. Okay, so you switch on the microscope and afterwards you switch on the software, everything starts up, and this is the first window that you see. The window separates into three parts. On the right hand side, the image is being displayed, where you also have some options of in which way this image is being displayed. In the center, you set up your beam path. If you are also familiar with ConFocus software from Leica, it's basically the same, just that the way of setting up the beam path is a little bit different here with a wide field microscope. So here you also have a lamp, that usually would be an excitation laser with a ConFocus system, but here you have a white light lamp that then here via this orange line is showing you the beam path. And then you have below here fluorescent cubes, single band cubes. So if you mouse over, you can see that there's a certain excitation and emission spectrum. And this already by the color is indicating what kind of fluorophore you can detect with this kind of fluorescent filter cube. If we follow further the beam path, here you have the objective that you can also choose by clicking here onto this drop-down list. And then you have access to the 10x air objective, 20x air objective with a long working distance. And there's also a 63x oil objective. Good. You can switch between those by just here activating the drop-down list. And the red one is the one that's active. And then you can click here on the 10x. And the microscope is switching automatically from 20x to 10x. You can also use those buttons here on the very left side. But yeah, in the end, sometimes there are several ways of achieving the stuff that you want to do. There are slight differences, but I come to this during the training. For example, why are there 3 buttons to acquire an image? But this is something for later. On the left-hand side here, this is the part where you can set up how fast, in which way the image is being recorded, meaning those are usually camera settings or light source settings. Here on top is the so-called acquisition mode. The acquisition mode actually allows you to decide what kind of dimension I'm going to record. It's a camera-based microscope, so you have always a camera chip that is being read out, and there you have always an X and Y image. The question now is, do we want to add the Z dimension, so move along the Z axis? If you click on this button, the dialog for the Z stack pops up. This is also something that should be familiar from the ConFocus system, where you set up beginning and end of a Z stack. And by activating or deactivating it, this dialog shows up or is hidden, because if you don't need to acquire a Z stack, why should you see the dialog? And then you also have the option to do a time series. The time series works also in a quite familiar way, that you have the option here to minimize the acquisition. This means the system will try to record the images as fast as possible. Here already estimating what would be the time for a single frame. This can also vary. If you go for minimize, the system will try to speed up where it's possible. You also have the possibility to have control the duration of the time series. This, for example, here can be checked with inquire until stopped. This is an option that I usually don't suggest to use, because there are some pitfalls later on in the data structure. That's why I usually say, please, if you want to do a time series, go with the duration of the experiment. For example, if you know, okay, my experiment will take around 30 seconds, but it might be that I start the experiment, or that I can add maybe the liquid to the experiment a little bit later. So just go for a minute, okay? Just by typing in, activating here over the minute, type in 1, and then a 0, and a 0, and then the system will also automatically calculate how many cycles will be imaged. So cycles mean how often the time series starts from the beginning. If you have, for example, here a multi-channel experiment. Right now we only have one channel, and within 1 minute, 650 images can be acquired. Or you say, I want to image for 1 minute, but I want to have a certain amount of cycles within that minute, maybe only 300. Then you have to uncheck minimize, for example, and still want to go for a minute. And then it should also be clear that you need to increase here the time that you need to spend. Basically, it's double the amount. So you would go for 180. It'd be close to 1 minute. Okay, this is stuff that you can also manipulate or control. And of course, you can also activate both settings together. So create a Z stack that you image over time. Okay, and if you have set up a Z stack, this time it will take in order to acquire a Z stack will also be implemented here in the minimize function. So if it takes 30 seconds to acquire a Z stack, it will also have here as a minimum time 30 seconds. Okay. Good, because then per time point you will not have a single image, but a single Z stack, and this takes a certain amount of time. Good. For now, this, let's say, is can sound quite complex, but of course this is dependent on what kind of experiment you are planning and what you would like to quantify afterwards. Down below the acquisition mode, we have here the image exposure functions. Those are actually the control over the camera. So how long is the camera chip being exposed with the emitted light from your sample? Here you can have, for instance, usually maybe start with an exposure time of 10 or 20 milliseconds, especially when you're using DAPI, because you don't want to expose too long with your UV light. And also DAPI is usually quite a strong fluorophore or staining that you shouldn't waste time here. Maybe I just click on live and to show you, okay, we have a sample currently on the microscope. And if I go here to, just for contrast reasons, I will switch the color to cyan. Okay, and those are actually nuclei being stained with DAPI. I'm now activating the Z function because with this I can remotely control then also the focus here. Right now I am manipulating the focus. Okay, you can see this here. That's quite cool. Maybe something to learn for image acquisition. For example, if I ask you now, or it's a general point for either fixed samples or living samples, you don't want to fry your sample, but you also don't want to have a bad quality. In the end, you have to balance image quality with also the intention of the experiment and of course the viability of your sample. Viability means in that case either the fluorophores are being bleached and fade away, or the cells die because you are exposing them for too long with too much of light intensity. So the thing would be you want to have a robust balance between signal to background to have a decent image quality, but also not to kill your cells. Cells or samples in general. I don't know with what kind of specimen you are working. However, as I said in the beginning, you could usually start with 10 milliseconds exposure time. How do I know if the image has a decent quality? Well, let me show you by using a different magnification. And then we talk about image quality. Okay, so I go to live. And here now we see nuclei. So what you can see here, for example, an experiment could be how many nuclei do I see? Okay, so this is the way. It's not about the beautiful image that you get with our microscope. It's about really completing the workflow and to learn how many cells do I see? What kind of cell density, for example, do I have in this specific field of view? So the point that you need to quantify is the amount of nuclei, and those need to be segmented because you want to count them individually. So you need to have a certain image quality. There are now, let's say, more old school ways of doing imaging, and this would be you have to fill the full dynamic range of your camera chip. What does it mean? Well, your camera chip is a 16-bit camera chip, and it can detect differences intensity differences in over 65,000 nuances. Okay, this is quite good because if you have in a single field of view a very intense nucleus, for example, consider a neuron. If you have a nucleus that is quite bright, but then you have those projections, they are very faint or very dim in their signal intensity. Still, they have signal. But it might be that the signal differences between the projection and the nucleus can be, I don't know, 400-fold or 500-fold. Okay, and now consider an 8-bit chip that you usually have, for example, on confocal microscopes. An 8-bit chip means that it can distinguish intensity differences in 255 individual steps. If you would now have a projection that has the intensity value of, I don't know, 10, and the nucleus is 400 times brighter, you are already exceeding the dynamic range of the detector. The cool thing now happens with a 16-bit, where you have just a broader dynamic range. It actually allows you to see, on the one hand side, the projection and the nucleus, and both are not either over or under saturated. Okay, this is quite nice. This means what dynamic range is actually all about. For your image and your segmentation later on, it's very important to have a good signal to background or signal to noise ratio. This means how nicely can you see the nucleus compared to the background. Okay, and here in this image you would say, well, it's actually quite nice. If you now have a look here onto the left-hand side, you can see here the dynamic range from 65,000 to 0. And then you see those gray bars here. They're actually showing to you the darkest and the brightest pixel of the image. If you want to see how the image really looks on the camera chip, it looks basically like this. Okay, if I now use the full dynamic range, I can also show this to you here on a histogram. You can see here the distribution of all the pixels in the image. So we have all of the pixels basically being present in the first part of the dynamic range, and then the rest here is empty. Now somebody could say, yeah, so if it's empty, please increase the exposure time or light intensity so that we can fill here the full dynamic range of the chip. Let me do this. So now I'm increasing the exposure time tenfold. Okay, now we're at 100 milliseconds. And still most of the pixels are here in the first area of, or the first part of the dynamic range of the chip. And let me do this now with 1 second. So what you can see is now this was too much, okay? All of the pixels are basically saturated and they are here on the right-hand side of the spectrum. So this was a little bit too much. The point that I want to make is actually less complex. So half, still too much. Maybe like this. Now it's not being displayed. Ah, here we are. Okay, this is the distribution of the pixels. And maybe going back to 100 and then so like this. Now you fill the full dynamic range of the chip. Let me acquire here an image, okay? I just click on single image, and this is also for you to learn. Clicking on single image acquires a single image of the currently active channel. We have only one channel active, so single image captures just a single image. And it is being saved, not here in this acquisition mode, but here in open projects. Every time you click on single image, capture image, or start, a folder is being created if you haven't created your first one in the beginning, and then here's the image 001 being saved. Okay, this is the image that we just recorded. Good. If I now record another image, it will be called image 2. Okay, so that's an ongoing enumeration of the images. I will also uncheck the Thunder functionality for now because we don't need this currently. And if I now click on single image, you just get image 3. Okay. So in order to quantify the nuclei, this image should be fairly sufficient. But what if I challenge this point now and say, yeah, of course, this image is sufficient to quantify your nuclei, but was the time it took to take and the intensity of light that you put into the sample, was it necessary? Of course, for a single image, it doesn't matter at all. But when it starts mattering is when you either do a time-lapse measurement or do you want to scan a huge area, a huge field of view. Maybe you want to scan the full slide. If this takes, I don't know, 10,000 images, it is a difference whether whether a single image takes 100 milliseconds or only 10 milliseconds. Okay, and if the information content is still the same, why would you go for a high light intensity and a long exposure time if it's not necessary? And this is the cool thing with the camera that you are using. It's an CMOS camera, 16-bit, and it allows you, due to the low background noise, also to have a decent signal-to-noise ratio, so nuclei versus background, and then allows you to quantify the stuff. So let me compare this here. If I now go here to 10 milliseconds, and I record a single image. Okay, here, again, I will go here to the full dynamic range. It looks darker, the image, but it's anyway just a depiction here of a 16-bit image on an 8-bit monitor screen that you are currently looking at. That's why we have here this automatic button. If you go to auto scaling, it automatically switches to highest or brightest pixel and darkest pixel. And you still see, yeah, the information is actually still the same. Only if the first quarter of the chip is being used, but still the information content is more or less the same. So now going below 10 milliseconds would also be possible. You could also exposure, for example, for 5 milliseconds, recording an image, and you see, maybe a sixth of the chip is being used, or the dynamic range, and still I can see and count the nuclei. So the next point would be, you can even reduce the light intensity that you use. Now we are at 30% of the incoming light, and this is the next feature that you can learn here. This is the FIM, Fluorescence Intensity Manager. This is a metal grid that sits in the back of the microscope where the light guide from the light source is coming in. And this allows you to shade or to catch a certain percentage of light that is coming into the microscope. So if you have very sensitive cells or a very bright staining, as in this case here, you can also reduce the light intensity that you bring to the sample. This is also important if you want to go for autofocusing, for example, because autofocusing also puts a lot of light onto the sample. So here now we are at 30% and of the incoming light intensity and 5 milliseconds exposure. And what you can see here, still the image looks the same. Okay. I will now close here the histogram and I will show to you side by side what is going on here. If you click, by the way, here on plus, you can create new windows. And here you can open up this window to have a bigger area for the individual images. If I click here on the first channel, you see here in red what kind of image is being used. So here we have the 100 milliseconds, 100%. Or was it that one? This was saturated, this one. And now the second image, 10 milliseconds, 100%. And the third image, 5 milliseconds and 30%. So from far away, and we did now hear the auto scaling, so switching to the brightest pixel always, brightest and darkest pixel. And if I link all of those images, then I can control all of them. And you have now a look here at 100% view. Can you spot a difference between maximum laser intensity for 100 milliseconds or 30% of laser intensity and 5 milliseconds exposure? I have a hard time doing that. And still, you have quite a nice dynamic range, because where you can see this, here on the left-hand side is not only those small buttons that show you the brightest and darkest pixels, also those values are given, okay? The brightest pixel in the shortest exposure here is 1400 as an intensity value. And the darkest pixel, so the background, is 200. What always gives you a rough estimate is if you divide the smaller number by the bigger number. So here it's a signal to background ratio of 7:1, roughly. And this is a value that you can optimize your imaging settings with. For example, if you don't know how long you should expose your image, have a look, activate the auto scaling, and check what is the brightest pixel and what is the darkest pixel. Okay, of course, it needs to be part of your signal. If you have antibody residuals and they are super bright and the structure is super faint, mouse over the structure and then down below. I'll show to you here. Now it's going away. So here in this area, I mark this. There will be now an intensity value popping up telling you how big or how high the intensity is, where the mouse is at the point. So it's now at 700. Okay, and now if you move here, it's at 200. So you divide those values and you know, okay, the image or the signal to background ratio is somewhere between 7:1 and 3:1. Still, this is more than enough to segment those kind of nuclei. What is the point I want to make? First of all, you have the option to control the light intensity that is coming from the light source and also the exposure time. If you don't know your sample, always approach the image settings or with the image settings from below. So start with a maybe too short exposure time and don't see very much, and then increase either exposure time or light intensity, depending on what the intention of your experiment is. If you want to do a 48-hour time lapse, you have to have very self-friendly exposure settings. This means you have a very low light dosage that you put onto the sample, and maybe go for a longer exposure time, because it's usually healthier for cells if they have a low continuous light intensity put to them instead of having a short burst of super high intensity light. Okay. This is something that you need to experience over time with the kind of sample that you are imaging. So this is the most important thing. And also keep in mind, with using the auto scaling button, it allows you to display the image that you can judge whether the image quality is good or bad. Okay, by just creating a rough ratio between the brightest and the darkest pixel. This will become also important later on if we want to use the Thunder functionality, where, of course, the quality of the image or of the result is dependent also on the input image quality. Good. So far, are there any questions? Am I being too fast, or am I explaining too much? Is it not necessary? Did you all know this already? Can I have a small feedback maybe?
For me, it's very good so far.
All right. Also for those, maybe you don't have a headset currently, or you don't have a microphone. There's also a chat function. If you move around your mouse, there is this small bubble with text inside. There you can click on, and then a chat window will open. And there you can also type in questions that you have. Okay, and then Patrick can intervene and ask the question if there's a question coming up. Good. If there are no further questions up till now, we just proceed. Okay, so we talked about the illumination settings where you can control with a so-called fluorescence intensity manager the amount of light that is being put onto your sample. Then here there's another advanced control that you have over the ILFLD. What does it mean? Incident light field diaphragm. This is the shape with which the sample is being illuminated. Let me demonstrate this. Right now we have size 5, a circular structure. You don't see anything. If I now reduce this field diaphragm to size 2, you can see already here the circular field diaphragm. With this, you can only actually expose if you want to do a single field of view and you are only interested in, I don't know, 5 cells here in the center. Why should you expose with the light this whole area where the cells are growing in? You don't want to harm all of them, just the ones they're doing the experiment with. Okay, you could go even smaller. Yeah, and then only a very small part of the field of view is being imaged. This allows you to reduce photo damage to all the other cells that are growing inside your field of view. Of course, then you cannot do a tile scan, for example, but if you have a single position experiment, might be worth a try. So we have here different sizes in a circular shape from 1 to 6. And if you go here even further below, there is size 5 square. And I don't know, and now it just comes to my mind that maybe you are just sitting in front of your 13-inch laptop screen. We can also increase the magnification of the software here. And hopefully you can see better now. I could go to size 2 square, and that's just a square window. Okay, so you get the idea of what the field diaphragm is doing. All right. Good. Next thing, magnification. Or maybe put it into layman's terms, you don't need to use the advanced settings. You can also go for standard, and then you only have control over the fluorescence intensity manager. This, maybe if you get confused in an easy way, maybe you put it to standard, and then you don't need to worry about the field diaphragm. Usually this is also not necessary. Magnification here, again, you can switch between objectives, and I can briefly explain what is the difference between those magnification buttons and this drop-down list of objectives. If I go to live and I want to switch to the 10x objective, here I cannot use the drop-down list anymore in the center, but I can still use those magnification buttons. Okay, and then the image builds up and is using here the 10x objective. Okay, this is here why those buttons might also still be important when you are being in live and then want to switch objectives. Good. And the next functionality is coming in, Thunder. You might have heard about it already quite often. For the people who are sitting during the demo, I think Patrick, if I'm not mistaken, Marco was doing the demo, so the people are already excited to use this new functionality.
Yes, Marco did and used, but I'm not sure whether all people joined. At least Herman himself was available at the time.
Good. So what does Thunder do? Thunder's core method, maybe I share for a second. This is multi-screen applications now. Robert, I will now share for a second my own screen here on the laptop. You don't need to exit because I can just overrule you. And I brought a small presentation just for the people who weren't around during the demo. Just briefly want to explain what is computational clearing doing, because the core technology behind Thunder imagers is computational clearing. The problem with wide field microscopes is that they are illuminating the full sample, okay? Meaning, even though you have a very precise optical sectioning with your objective, the problem is that the light that is coming from out of focus areas that are not in the center of the focus plane here in the objective is not being excluded. Okay, if you would have, for example, a confocal microscope, this light would be blocked by the pinhole, but we don't have a pinhole in wide field microscopes. This means that the thicker the sample gets, more of this stray light is overlapping the signal in your focus plane. And this is then in the end hiding the structures of the specimen that you are imaging. So it gets worse the thicker the sample gets. Okay, so now with the single cells that we were imaging right now, this can already be a little bit problematic, because in a second I will come to this. There was already background light that was overlaying or superimposed onto your nuclei stains. And what computational clearing does is that it can in real time calculate what kind of information is being recorded from the focus plane of the objective and what kind of light is coming from the out of focus planes. And this light here is excluded from the image that is being displayed. The cool thing is that there's nothing to calibrate. For example, there are other methods that can improve the image quality, like, of course, the confocal. But for wide field microscopes, you could also use, for example, structured illumination. The problem here is that you would need actually to calibrate onto different kinds of cover glass thicknesses and materials that you have. This you don't need to do with the Thunder imager. Here you just activate the function, and you can see here side by side for each individual image, the light that is coming from out of focus planes is being excluded. And a very big plus, and you can always, and we will also have a look on to this feature, you always have a raw data set. So if you think that this kind of image quality is so insanely good that it might be something artificial, just have a look into the original file, okay? And convince yourself. There, I will just use 3 slides to explain this here. Optical system improvement or image improvement in the end, there are 2 broad ways. One is an inclusive approach where you use deconvolution, meaning you calculate the stray light here on top and below the focus plane of the objective. You calculate this light back into its point of origin. It's quite easy when you have only a single fluorophore or a single spot that is creating this kind of scattered light. But if you have, for example, 1 million of those pretty close together, it's a problem to distinguish where is the light originally coming from. So the thicker the sample or the more background you have, the longer it takes to do the convolution, and also the less good the results get. What the people did then in the past was creating or using a pinhole. Of course, then here the point spread function looks a little bit different. But in the end, what is being done is that we block the light that is coming from out of focus planes. And something comparable computational clearing is doing, just without a pinhole. And what kind of functionality you got with the Thunder imager is not only having this exclusive improvement that is called instant computational clearing. This is the method that works on individual images and also in real time. So once your Z stack is done, also the computational clearing stack is done. We also offer you, for example, here a large volume computational clearing where we combine the exclusive improvement of the image. And once we are done, we are doing a 3D deconvolution on top. What does this mean for your image itself? So you need to extrapolate to your kind of samples that you are using, okay? So in your raw image, you have here, for example, a fluorescent bead. This is one I acquired last year during February during a workshop. You have here the lateral view of a fluorescent bead. And this is then I record a Z-stack, and you see here, hopefully, nicely the stray light of, or in the end, the point spread function of this structure. If we now do instant computational clearing, we remove the light that is coming from out of focus planes. So hopefully you can see that here the yeah, quite a substantial amount of the stray light that is being present in the lateral view is gone, but the structure itself did not change. Okay, the same is true also in the lateral view here in the axial view. Sorry, where you have still the along the z-axis here the distortion of the bead nicely visible, but most of the out of focus light here is gone. If you now do on top of this data set here a 3D deconvolution, you can further increase the quality of the image. Okay, and also then see now you are changing the structure because the light that is being distorted due to the optical system that you are using is being calculated back into its point of origin. The structure gets, in comparison to the original, higher resolved in quotation marks, because resolution would be defined by having two objects being separated from each other. The point I want to make here is you have both functionalities around. If you want to just improve your 2D imaging, use instant computational clearing. It's just a click of a button. I will show it to you in a second. And this one here, large volume computational clearing, is also not very complex, because you also, in the end, if you're not experienced enough with 3D deconvolution, it's super easy to start with it, because most of the input that you require is done by the system, because it's based on the opto-digital properties of your setup. So yeah, it's very easy to use and also quite fast, because once you have less light to being calculated back into its point of origin, this also speeds up your deconvolution. Good. At this point, I stop. Yeah. And Robert, if you could again, please share your microscope screen. We come back. Perfect. Thank you. All right. Here again, just to check. Yeah, I need to request the control again. Sorry. Thank you, Robert. All right. So here we have the Thunder functionality. You see here this flash icon that you saw. The problem was we didn't know an icon for a Thunder sound. If you have an idea, call me, please. So here, when you have a lightning happening, there's also thunder. That's why this is the icon. The only thing that you need to do to improve the image is click on this button. That's it. There are settings here that pop up and seem to ask you for input, but for this functionality, it's not necessary, because those features don't play a role in the computational clearing. Okay. And here you have this zebrafish embryo again, large volume computational clearing. If you activate this, it tells you, you're using a single plane. Keep in mind, large volume computational clearing combines computational clearing, so the removal of background light, and 3D deconvolution. And 3D means you need a Z-stack for that. Okay, that's why here you could do it, but of course it's then just computational clearing. Good. Going to live. Just check here. This is the image, and let's just have a look. What do you see? You see a lot of nuclei, but you also see those shades here, for example. What are those? Those are actually areas where above the focus plane of the objective, there's some debris. Maybe there's a cell that was detached and then fixed onto a different layer, or there's some dirt or dust that was enclosed when the cover glass was put onto the fixed cells. Who knows? Problem is, it's creating quite a mess in your image. And depending on how strong the signal is, you might get problems with segmenting those cells, for example. Okay, so let me show you what now Thunder can do. Okay, so I'm not doing any input here. We have this is 10x objective exactly. I activate it and I just click on single image. What happens is immediately the Thunder image is being displayed. But if we go here back to projects, this is something that you already saw before. The red image is the one being displayed. This is the original image. And now we set those side by side. The right-hand side, we click here on the thunder image. And what you can see is that the amount of light is quite drastically reduced in the thunder imager. Of course, we are not computationally clearing itself. Yeah, please keep in mind, this is maybe also a take-home message. What we are doing here is separating the in-focus information from the objective plane from the out-of-focus information. The 10x objective has quite a big focus volume. So if everything here is in focus and in the focus volume here, in this case, nuclei, you don't see any improvement in the image itself, so in the structure, because the structure itself was perfectly captured beforehand already. The problem that we had in the image was light that was coming from out of focus planes. And this is what thunder imagers do. Okay. Or the computational clearing functionality. You now see here those cells can be easily segmented because here this blob is away. So it's not a problem anymore to segment those cells here that were superimposed with this dirt blur maybe that was going on there. So for two-dimensional cells, you can get rid of most of this background light that's coming from out of focus planes. Of course, it is not removing if you have a fabric that is also inside the focus plane of your objective. This, of course, cannot be removed because in the image itself, it was in focus, okay? So it was not an information that was coming from out of focus planes. It's not doing miracles, but I think it's pretty close to them. It gets really interesting the thicker your sample gets. And then also the 3D deconvolution kicks in and allows you a drastic improvement of the image. And before we come to that, I again ask, are there further questions? Otherwise, we are proceeding to more complex experiments.
There's one question, Falco, from Herman coming. If position 5 in the field diagram or the diaphragm covers the entire field of view, when do you need to position 6?
Never. There is a difference, or why do we need even bigger sizes? The reason is the eyepieces that you have a bigger field of view than the camera chip. Okay, and while the camera chip is now already fully illuminated with the light on field diaphragm size 5 or even 4, it can be that, it is definitely the case that if you look through the eyepieces, that you just see the ring as we saw it when we had here the field diaphragm closed. So you're not illuminating the full field of view for the eyepieces. The field of view diameter for the eyepieces is 23 millimeters, and for the camera chip is 19. So there is a small offset between the area that you can observe with the eyepieces compared to the camera. And for example, if you just want to quick check cell flasks, for example, and you don't want to document, you just want to acquire images, use the eyepieces, you need to open the field diaphragm to a bigger size. That's
Thank you, Falco.
The question. All right. Good. Yeah. What I usually tell also the people when we come to the training is just activate the thunder image or the instant computational clearing and just see what it does for your image. If your samples are that perfect that you don't need this, perfectly fine. The time you go 3-dimensional, you will love this feature. I can promise you already. Okay, now all of the stuff that I just explained was with a single image. Okay, with a single image. Yes, a single image, and also with a single channel. What else could we do? We could also set up a multi-channel experiment. And Robert was so kind to bring a sample here that has, in fact, 3 colors. So 3 labels that we can observe here. And why don't we have a closer look to that? Okay, so increasing the magnification and going to live again. And I will also focus. something like this. There is a small step size or a minimum step size that I have to take with this remote control. And at some point, I might ask Robert to fine focus, but for this now it works. Again, here we check. The brightest pixel is 1300. The darkest is 200, so it's roughly 6:1 as a signal to background ratio, which is also for the Thunder and computational clearing methods super nice. Maybe here a rule of thumb would be between 4:1 and 10:1. The quality of the processing is best. Everything above 10:1 actually doesn't change anything anymore in your image, and everything below 4:1 can be critical in terms of image quality that you will get. This is something to note, maybe. Good, multi-channel experiment. Here we see the DAPI stained nuclei. Now we want to also explore the GFP and the Texas red fluorophores or structures and signals. How do you create a multi-channel experiment? Pretty easy here in the setup of the beam path. Let me just reduce that. In the setup of the beam path, you can press plus. And then the beforehand here, channel 1, is just being duplicated with a different color. But if you have here a look at what kind of fluorocube is active, they're identical. Okay, so if you want to image with this channel, okay, by the lamp, the green or GFP fluorophores, you need to activate by clicking here the GFP fluorocube. Okay, and now you have two separate channels. One channel is the DAPI channel, and the second channel is the GFP channel. And now we also want to see the red channel. So we're just clicking on plus and then activating the Texas red. Okay. Again, for contrast reasons on your screens, I will turn to magenta for that. Okay, good. And now we need to set up the options or the properties of the individual channels. So for channel DAPI, we have exposure 5 milliseconds and the input intensity is 30%. Image is quite nice. Good. Maybe we go here to 10, just to have even more light, even better separate or signal to background here. Now we are above 10:1. Second channel, 5 milliseconds, 17% input light. We can see the cells, definitely, but you can also see that there's a certain dynamic range of the fluorophores or of the signal that we see. We have cells that are quite bright, expressing presumably GFP to a quite big amount, and then there are cells that are faintly expressing that, and we want to catch both of them. The problem is that the background here in relation is quite high. So we have a background of 160 and the strongest signal of 290. So here if we mouse over, we see the intensity is 215 and 200. So here are only 15 intensity values difference between those cells. It might be possible, yeah, if we just acquire now an image, single image, that we see this image already here. Now the Thunder image, you can see, we can still see a nice dark background and those cells being still present. Of course, they are on focus, but the dynamic range is quite bad. And then you see that this image looks quite granular if you zoom into the 100% view. So what I suggest is, we go back to live. First thing is, as I said, yeah, start from below. Now we can go maybe to 50 milliseconds, 10 times longer. Yeah, and it seems to be better now. We are using, and that's also why I didn't, first of all, increase the light intensity. 50 milliseconds is still a decent value for exposing an image. But if you have cells that are expressing a certain fluorophore that differently, you don't want to increase the light intensity because it might be the risk that you are losing those cells here because you are bleaching the fluorophores, okay? That's why it might make more sense here to go maybe to 60 milliseconds to get a decent ratio. Now 1,300 to 177, so let's say 6:1 roughly. And what I said before, this is now the strongest signal. If you want to consider your faint cells, you are now at 340 and still to 200. So you're now 2:1 in terms of signal to background ratio. So why don't we go to 30% or even 55% fluorescence intensity manager and have a look? Again, the image looks the same, right? It's the same discussion that we had before. The problem now is that we have a big dynamic range. Here we are 4,000 fluorescence intensity, and our image itself is 800 and the background is 230. So we are now at 4:1, and it's for this image now, we don't want to overdo it, more than enough. Good. So now we have optimized settings for our GFP channel. Magenta, so the Texas red. There's nothing to see. But we had the problem beforehand as well that Texas red in this case was fading away quite easily. So I will go down maybe to 30% and 100 milliseconds exposure time. And Robert, if you could now use the sticks, please, to move to a different position on the stage, just where we have more labeling. There it was. Yeah, we were imaging hard beforehand. Yeah. Yeah, maybe. Yeah, this will fit now. Thanks. Good. So here you can see the signal. And 1,000 to 200, so it's 5:1. If we move over it, we are at 600 to 200, 3:1. We could get a little bit better, but you see here those empty positions where I was using beforehand 100% of light intensity and also 100 milliseconds exposure time. Far too long exposure with too much light. Your Texas red was being depleted. I use this here for focusing. So this tells you a lot about your sample. So that it likes less light intensity. So I will even reduce it and sacrifice now light intensity by or with a longer exposure time. Okay, so we didn't change much, but now we have a 5:1 ratio roughly, and we are using not much light intensity. This is better in the long run for this kind of fluorophore right now. If you explore your sample and you see, my RFP or my Leica fluor staining was so nice this time, of course you can again go down with your exposure time, increase the light intensity. If your fluorophores are not bleeding or bleaching, lucky you. In this case, we are already adjusting to the specimen that we are having. Okay. And now, since we have everything set up, all different channels, we are not using the button single image that I was using beforehand all the time, because single image acquires the image of the currently active channel, and currently only the RFP or Texas red channel is active. If I now go to capture image, it switches back to the DAPI, acquires an image, then green, and then red. So it acquires all the different channels. And what you see here is automatically being displayed the thunder image, okay, where a lot of this background light is already being excluded. And if we go back here to the folder, we go back to the original image, that would be actually here the original image. And this is the thunder image. Yeah, in a side-by-side view. And you can see here those obviously background light contaminated areas that are pretty clear and see-through in the computationally cleared image. Good. So this is now a multi-channel experiment. Now let us step up the game. And the next thing would be, because the sample that we are currently imaging is a cell slide. So a glass slide where some cells were grown on and then fixed, and then, yeah, we are imaging them today. I'm switching back to 10x. And it might be the case that, first of all, if you want to have a decent statistic, you want to increase the number of cells that you are counting. Or if you want to get an impression of, do you create a certain, in this case, actin filament phenotype because of a certain mutation that you inserted, or because of a virus that you were using in order to transfect the cells with a certain, I don't know, what you ever imagine. It might be reasonable to have either multiple fields of views, distributed over the area of the slide, or you just scan as big of an area as you can get. And for this, we have a nice program that is called the LASX Navigator. And this you can find here on top. I bet on your SP, what is it, an SPE confocal?
Yes, SPE.
Yeah. You probably don't have the navigator, or do you?
No, we don't.
Okay, yeah. So here you will see and learn a nice new feature. The navigator is pretty close to the function you might know, and this is the stage experiment function. But navigator is like stage experiments on steroids. If I click on that, we are entering a new surface, okay? That here are already images from beforehand, and I will delete all of that to explain what do you see. I will also get rid of my face. So, okay, so what do you see here? First of all, let this new software surface sink in and have a look. Okay, do you recognize some areas that you might be familiar with? First of all, you have the live button. That's good. You have single image, capture image, spiral. What's that? We talk about that in a second. Then you have preview and start. Those things here are actually buttons you already know. Live button, single image, capture image. And start would actually be if you set up a time-lapse experiment, or a mosaic scan, or a Z-stack, you start this image acquisition or this acquisition of the data set with the button start. Okay, so then here are some obviously drawing tools that you can use. We come to this in a second. And then here on the left-hand side, if you have a closer look, Falco was talking about beam path before. Yes, I was. And those icons are hiding the user interface profiles from before, but you are free to choose whether you want to display them or not. Okay, you can activate them or deactivate them. The navigator focuses on image acquisition over bigger areas. So if you have set up in the normal user interface that we have just been to, you set up your multi-channel experiment, you don't need to enter this anymore. Okay, it's fixed, it's set up, it's robust, it's working. Same goes for the imaging settings. Exposure time for each channel is already set. We have checked those features. Same goes for illumination. Thunder is active, we had this. And then here are project settings that are for now not relevant yet. Here are stage settings. Yes. Navigator is combining normal imaging with stage features that you can do this over bigger area scans. And carrier will become very interesting soon. All right, good. And now the big central playground, as I call it. What you can see here as the white rectangle is the field of view of your camera. Okay, currently we are using a 10x objective. And this field of view is live. Okay, this means if Robert, if you would please now move the stage a little bit up and down or left and right on the joystick, you see how this movement is directly translated into the software surface. Okay, and this, of course, you can also combine if I click on live. And Robert, if you now would do this again, please. Yeah, you can see how this is then also changing live in the software surface, which is super cool. If I now at some point click on stop, and Robert is not moving anymore, then here it also stops moving. So this white square is showing you where the field of view of your camera is. You can always fly back to this field of view if you click on this button here on top. Okay, move to stage position. If I click on that, I'm flying into this. Good. Now I use my mouse wheel to zoom out. And this is like Google Maps, for example. Yeah, I can zoom out and zoom out and zoom out. Okay. At some point you see this right gray rectangle. And this is the full playground that you have. This is the stage area where you can move to. This is the area where you can set up as many experiments as you want, depending on your sample is as big as this field of view or the stage movement area. Currently, we have quite a small sample that compared to the stage area is maybe a size like this. We will see this in a second. And again, if I click here on the button, move to stage position, we are flying in again. Okay, quite cool feature. Now, I want to different experiment now. I will go to the Z stack and check if I can focus here. Okay, like this. Okay, and now you see all the nuclei. Now it might be that for the experiment that I'm doing, I'm looking for cell division cell divisions. Okay, so those normal standard nuclei are not interesting for you. You are looking for individual stages of cell division. Okay, so you need to check either by eye individual positions or create a huge overview to find where are the interesting positions that I need for my experiment. How would you do that? First of all, use an objective with a low magnification, in this case the 10x. Okay, and now we are going to live and zoom out a little bit. And now I click spiral. And spiral is the spiral scan. And the spiral scan actually means that you are running around in a spiral. Actually, not you are, the system is doing it for you until you press stop or until the full area is covered. Okay. And here you can see here we are already at the edge of the cell slide. So what you do when you see this kind of edge is, okay, I stop here. I know, okay, this is the area of my cell. Okay. So by using here down a circular tool, could actually create a field of view that looks like this. Okay. And you could also create, I will do it like this, a preview. Over this whole field of view and see where the areas that are not interesting for my imaging and which areas are interesting for my imaging. For example, here you see some residual nail polish. This is problematic. So here the image quality will be bad anyway, so you leave those areas out, okay, by default. Okay, so this were just a few seconds. I was not even recording this. This is just, as I said, it's a playground. It's for you. I will also delete this region of interest. It's just for you to see, okay, now we have a look at the full area here. And since we have such bright areas, the auto contrasting is not working so nicely. What do? We just click here on top and manipulate this on our own. Okay, and now we can already nicely see, okay, this is my cell area or this area that I can use for imaging. And this is what the navigator is good for. Right now we have a little bit of, at least on my side here, a little bit of frame drops if I move around it. But the navigator can actually seamlessly zoom in and out because it's using different layers of resolution and then displaying it. Here on top, you always see what kind of resolution are we currently in. So this is now 136%. So this would be the one-to-one view, 100% view. This is what we just acquired. Okay, nothing is standard. It's just for you to know, okay, now I can select where are my regions of interest. You also don't want to image, for example, this empty area here. Why should you? Okay. So let us now create a few regions of interest. Maybe I just create keep in mind you can put in as many as you want. You could create here field of view. Okay. You could have here field of view. And you could have a field of view over here. Okay. And what you can see here is that the regions of interest that I have drawn is now automatically filled with the fields of view it would require for the 10x objective in this current setup to fill this area. Now, if I go to image and change the magnification, the regions of interest stay the same, but what updates are the fields of views that you need in order to fill this area of interest with the fields of view with the 20x objective. Okay, this is quite cool. All of the different regions of interest are given here on the right-hand side in the task list. Okay, and if you now click on Start, the system would go and create the image subsequently of all the different regions of interest and would automatically also merge them. Okay, why do I know this? Well, there are some stage options that you can choose. And here is, first of all, acquire separate images per regions. That's fine. Optimized acquisition order of regions. What does it mean? For example, even though, so currently my camera is looking at this position here on top. I created maybe this one first, this second, and this as a third region of interest. If I now hit Start and would not have an optimized acquisition, it would start here with region 1, even though the movement takes longer than maybe to this area or to this area. And that's why the system will automatically make like a snake scan to optimize here the acquisition order. Next thing is what is very important for you, merge images during acquisition. This means once this tile scan was recorded, if this function here is active, it's also automatically merging the images. Okay, it's doing so for the raw data. If you want to use also, or if you also want to merge the Thunder images, you can do this later on with a button that I show you. But this is important. If you uncheck this, you will just acquire the individual images. Okay, that's just for you. So usually it makes sense to keep this function active. Also that you want to keep the raw data because, and this is very important for your whole scientific working anyway, always keep the raw data. Because from this raw data, you can always go back, you can check it, and you can redo some kind of processing or merging even. The blending function here is set to smooth. This is, from my experience, also for this kind of specimen, the best way of creating a merge image. Good. All right. For time reasons, I will skip the smaller areas and just go to the big one. Okay. And now I didn't do anything further to the image or to the region of interest. If I now click on Start, I bet we will have our time wasted, because what is very important when you do a tile scan over this big area that we are currently working in? Can somebody maybe unmute his or herself or type into the chat, what is a problem if I just now, as I set up this experiment, what is happening? What is important to keep in mind? Actually, everyone is already asleep. What I'm aiming at is focusing, okay? Because what I didn't check beforehand was whether the focus was perfectly set, yes or no. I was creating this overview with a 10x objective, and then I switched to a 20x objective, and I never checked the focus. What happens now is that probably the image that I get is crap. So maybe this was a little bit too quick. Here, you start when you click on the navigator, you start in the acquisition window. This is the acquisition workflow, and the next workflow would be the merging. So here we have the list of our images, and the last one that you created was this tile scan. And now if you have a look at the merge, nice and unsharp. Very good. And now you see also something else. there where the nail polish or some kind of the mounting medium was somehow creating a bubble, it's creating a lens effect. Yeah, you see this here? And this lens effect actually provides us with an even sharper image that we had before here in the other areas. It's going to be interesting once we are using the focus. Good. So then also, again, if you click on the Thunder image and merge this, the output is as bad as the input. Okay, this means that using the computational clearing will not rescue your image, because if the input image was never in focus, also the Thunder imager cannot do much more. But you can see here what would be maybe a go-to image quality that you would like to have. Good. So how do we improve our image here? Here's our tire scan. What we would need is a focus map, because we saw different things. We first of all saw, I will do it like this. Okay. What did we see? We see here, first of all, we are not at all in focus. And then we see that we have areas that are, yeah, completely on a different kind of focus. Okay, so there are two options now. Option one, we exclude this area because this problem here of the sample is inherited only to the sample, and it's super hard to get rid of this effect here. Okay, there will be, especially on the edges, you will get a bad image quality. So let me do this way and just move this field of view maybe to this area. Okay, so this is also what an overview image is good for, because now you see, yeah, this is an area where I don't want to image. Okay, now, but I want to, the rest of the cells should be in focus. So what could you do? First of all, we are here on top. First thing that you can do is double click to the point where you want to go, and the stage immediately moves there. That's quite cool. And then I go to move to stage position. Okay, and then I go to live and see, okay, where am I? I'm definitely out of focus. So I'm using here the focusing function again. And now, Robert, I would ask you to do the fine focus for me, please. Is that, yeah, perfect, good, that's good. Thank you. So now we have the perfect position. Now we could, yeah, do one thing and say, okay, we assume that all, so based on this position here, if I now click on start, all of the images will be acquired in this position. But just keep in mind that you would have some kind of tilted slide, tilted cover slip, or your cells are just not as even as you think. Okay, because with a 20x objective, you have already quite a small focus volume. So what you could do is that you actually create focus map points. And those are the buttons down below here. This was a little bit quick here. This light blue button is a focus map point. And the focus map point allows you to set a certain focus plane for the image that you are going to take. So if you click and activate it, you can set a focus point here. Actually, you can set focus points wherever you want. And I go for one in the middle. What is important to know is what happens with those focus map points. Currently, those focus map points only have an X and Y, so a lateral or have lateral coordinates. Where do I see those? If you click here on focus map, if you click on that, here are 5 points given with an X and Y coordinate. If I click on one, the stage moves there. We are not on live, so we don't see an image, but this is the positioning here. If I go to the central one I set up last, and I go to the live, you see, yeah, I'm still in focus. So you could click set Z, okay? And then go, for example, to the previous focus point and set there a focus, okay? This would be a manual way. What you could also do is set up the autofocus and let the autofocus search for the best focus plane. In my case, it's actually the best because my remote capabilities of doing fine focusing are very limited. So what I do here now is that I go to the autofocus settings and say, I want to have a certain capture range. This means the capture range is the volume in which the microscope looks for the perfect focus. But for this, you have to understand how the focusing works. The autofocus setting here, in this case, the so-called high-speed autofocus, is in quotation marks just doing a Z-stack. Okay, it's doing a Z-stack from top to bottom. You define the size of the Z-stack. This is the range. And depending on how many slices you use for this Z-stack, it depends whether you are doing the focusing fast or precise. Okay, just imagine you have a Z-stack over a range of 100 micrometers. You could be extremely fast if you only acquire an image every 20 microns. Okay, so 0, 20, 40, 60, 80, 100. But the probability to hit the focus with that kind of coarse setting is quite low. So the success rate of focusing will be bad. So you increase the precision, meaning you increase the number of steps that you separate those 100 microns into. For example, if you go for 100 individual steps, you would have a very precise focusing. It takes longer, but the probability to hit the focus is significantly higher. And this is what you can do here with those autofocus settings. You first of all set a range of the Z-stack. Here you need to know that from the focus plane we are currently in, a capture range of 20 microns means that it will go 10 microns up and 10 microns down. In total, 20 microns capture range. Okay, so if you know that you have a certain tilt into your within your sample, just go for maybe a slightly bigger range. Before we started here with the training, I was already playing around a little bit with Robert at the system, and we found that 20 microns is actually not enough. 20 microns was working, and that I usually suggest this, not the maximum precision, but the one beforehand, as the best way of finding the focus with those kind of samples. Okay, a lot of talking. Hit the button. I hit the button. Find remaining by autofocus. Now the system goes to the focus map points and is focusing itself through the Z-stack and then showing me the images and the focus. Yeah, here the Z position is then added. And this was done automatically. I didn't need to do anything. Except not going now to the stage position here on top. I go to the button next to it, move to tile acquisition region, meaning your region of interest. If I click on it, you see the full area that you are going to image. We have our focus points set. Okay, we have our multi-channel experiment set up. So basically everything is set up that we now can acquire a nice tile scan overview of this area with our 20x objective. So we hit start and let the system do the rest. Of course, now explaining all of the different steps took quite a long time, but this will be, of course, when you are sitting in front of the system, much faster because you don't need to explain to anyone how this is set up. But for you now, it's important to know, okay, what is the idea behind that? What is happening? And while the imaging, the image acquisition here is going on, I now adjusted the auto contrast, and you see here, this is the area where I have been imaging beforehand with Robert, where I was already bleaching the phalloidine staining here as well. This time it's not overlapping with the focus points here, but with this time I was doing here autofocusing with Cherry or with the Texas Red Cube, and this was obviously a bad idea. Again, thinking about the balance of exposure time and light intensity input and so on. Okay, but for now we are done. We go to Mosaic Merge. And we have a look here at our raw image. We are now at 20%, or 83%, 100%. Now let's have a look at our Thunder image. Quite nice, isn't it? And it's just, in quotation marks, computational clearing, meaning we didn't do any deconvolution or anything where you need a Z stack for, or yeah, we are just separating with a nice objective that we are using with a smaller focus area. We are separating the light that's coming from in focus planes from the out focus planes. Okay. Of course, next time we start with a fresh sample and then all of those bleaching areas are actually gone, but you get the idea. A very last point I want to make for those focus map points. Now we only have a tire scan of 20 tires. This is nothing. I think right now the biggest tire scan that I was doing was for 15,000 images. And this was, yeah, a ridiculous experiment, but there was a mouse that was frozen, so shock frozen with liquid nitrogen, and then it was cut into slices of 4 microns or 6 microns. And then each individual slice was laminated. And those laminated slices should be imaged. And we did this also with the navigator, created with a very low magnifying objective, a huge area of overview, and then went to the higher magnifying objective and were scanning the whole field of view. This means we used much more focus map points. So it's really, really important that you know how to use those focus map points, but not manually, but with using the autofocus function, okay? But keep in mind, those autofocus settings need to fit to your sample. And this example should also explain that the size of those tire scans can be different. And it also depends on your sample quality in the end. Also, this laminated one was very wavy. So the distribution of focus map points is then up to you. If you have an overview scan, it makes sense to follow certain areas. When you see there's a certain wave, that you can set there more focus points. Because what is happening, I'm not focusing on each and every image. You could do this as well, but this takes a lot of time and is not feasible for everyday imaging workflows. What happens with the focus map points is that here, to the lateral X and Y coordinate, you enter a Z coordinate. So you're creating a 3-dimensional point. If you have several of those points, you are creating a 3-dimensional map where you have the individual focus map points being laid out. And in between those focus map points, the height of the images that don't have their own focus points are being linearly extrapolated, okay? So if this one here is on 100 microns and this one on 80 microns, there's a 20 micron difference in between. So the image here will be taken at 100 microns and then 95, 90, 85, 80, and then you are on the other focus point, okay? So this is how the area in between those focus map points is covered, okay? Just something to let you know. So it's not necessary to set the focus map points super dense, okay? Because it's very unusual that you have this extremely uneven samples. Good. All right. That was a lot of talking until now. We still have half an hour to go. Another question to the chat or to the people around. Are there further questions?
Well, maybe just one small question. So with the computational clearing, the result, of course, is very impressive, but how sure are you that you're not removing any potential information rather than just out of focus light?
Yeah. So I cover this kind of training usually in the advanced training, but we can touch upon it. For this, I will go into the advanced settings to explain what is happening, okay? We are now back at the user interface, okay? And I go to processing because you can do a post-processing of your raw data set. So you can acquire all the data and then afterwards do the Thunder or the computational clearing. It's up to you. So for example, if we have here this image, okay, and we go here to the processing. You have the option here of instant computational clearing again. You could also have processing of the others, but right now we are focusing on the settings of instant computational clearing. Okay, so you see here two options. One is the feature scale and one is the strength. Okay, they are default values that are dependent on what kind of objective you're using. As I said in the beginning, or during the introduction of the computational clearing, computational clearing is an optodigital method. This means, yes, you have processing with algorithms on the one hand, but also those algorithms are fed with the real optical features and properties of your beam path. Okay, so it's important what kind of objective you're using, and this is all read out from the metadata and fed into this processing here. So this feature scale that you see here is actually based on the objective that was in use, okay? For example, and then there's, let's say a starting value given. This, in this case, is a feature scale of 8.5 microns. This is not just a random number. This depends on the objective. If you would change, for example, to a 10x objective, do we have such an image? Was it 10x? Or maybe we go to this one here. So yeah, what I want to say is it changes depending on what kind of magnification you are using. Also means that, of course, you would not create your other way. You would not expect to resolve actin filaments with a 5x objective, okay? And then just assume that, okay, if I use a 5x objective and just put the feature scale to, I don't know, 300 nanometer, it should detect actin filaments. This is not how it works. It depends, of course, also on the input image, so on the optic properties of your objective. So that's why we always have for each objective a certain value, a certain starting value, which from the experience works for 95% of the cases. Okay, so usually with those settings, you are not clipping, and that's the fear that you have, you are not clipping any data. Good. I just need to decide on a certain image. Let me have a look. Yeah, stay now with image 9. So this is our image. What you can see here is that you see for each individual channel, you can access those settings, okay? Because the structural feature that you have in each individual channel can be something different. You could have actin filaments and nuclei. The sizes are different of the structures, okay? And the default values give you a certain image quality. Now I didn't change anything, okay? And here I click reset and I apply. And so by pressing apply means please do the processing. So I do this, press apply, and it's done. So the processing is quite fast. Okay, the next thing is you can use those advanced settings to increase the image quality further. Okay, what does it mean? You can go for the structural features that are in your image. For example, here now we have this image, even though it's not 100% in focus, doesn't matter for now. You could activate here on top the micron, the scale bar, and just draw it here and then measure, okay, what's the size? 11 microns, okay? So the structures are actually bigger than what is given here. Okay, we can also now compare, and this is what I would use those advanced settings for. If you know that in general, your nuclei are around 10 microns in diameter, just type in 10,000, okay? The strength is the value of how much of the background light will be removed. We don't go to 100%. You could go to 100%, and still this doesn't mean that you create 0 pixels, okay? This is part of the whole processing. Is one algorithm that checks that there are no 0 pixels being created, because 0 pixels are very, very bad for image processing in general. So here we stay with 98, and this you can also play around with. Okay, as a rule of thumb for the feature scale, you shouldn't go for the smallest structure possible, but let's say for an average size. Okay, of the structure. Doesn't mean if now there are nuclei that are 20 microns in diameter, they will not be clipped from the image, of course. Yeah. Also the other way around. If there are now nuclei that are smaller, like those areas here, they will still present or will be still present in the resulting image. Let me just show this to you. Yeah, here they are still around. Okay. And this you can do for each and every channel. Okay, now first channel is 10 microns, and now we go to the second channel. And of course, again, this depends on how good is the optic or are the optics of your objective. And for example, the C-mount lenses, so the camera mount also has a lens inside to flatten the image, for example. This also takes into account of the distortion, and is taken into account by the computational clearing. Here, yeah, you have expression of GFP. I think this is not very specific as far as I remember. Here, so the cell size also is the limiting factor. So here again, I would also go for 10,000, maybe even bigger, because we're not only having the nucleus, but they are also in length a little bit bigger. So maybe we go for, and then there's the third channel, and this you can always activate and deactivate, actin filaments. Now the point is, you're not, you did also, or with the 20x objective, you are limited in resolving those actin filaments. So it might be a little bit tricky. So here you could also measure those structures, 4.5. But in the end, you know also the structure is smaller. But what I wouldn't do is here go for a smaller feature scale, because those are just agglomerates or accumulations of signal that you could not dissolve. So there is no reason in going smaller. That's why I would usually stay here with a default value. But for now, since we adjusted all the different settings, I will here also go now for a lower value, okay, 4,000 microns. And we'll just see how the adjusted settings impact the image quality, okay? So I will press apply now. All right. And now, as before, we will compare all the images. Good. So the point now is how good is the resolution for each of you? Maybe Robert, you were asking the question, right? Maybe you judge now how it appears to you, whether or not we were further improving the default settings. So in the left-hand side, you see the raw image. In the center, you see the default images that would be suggested by the system. And on the right-hand side, we were adjusting to the values of the structure.
Yeah, I didn't ask the question. I think it was
sorry.
that asked the question. But on this screen, I would say that the adjusted parameters maybe remove a little bit more light.
And especially, I guess, from the magenta channel, right?
Yeah.
This is the problematic one. And this is then really, the structures here are made up by much, much smaller structures. That's why it's better to use a bigger feature scale, because you would need to consider those bundles of filaments as the structure. And in the end, also, if you want to have the max, or if you want to set free the resolution power of an objective, you would need to use, first of all, a higher resolving objective, and then also doing a Z-stack where you then can also do 3D deconvolution on it. So using the large volume computational clearing, because we are only setting free, or we are moving light, we are not increasing the resolution with that. Okay, we are just removing background light with the instant computational clearing. This is something that everyone should keep in mind and take as a take-home message.
Maybe it would be interesting if we move to one of the samples that has not been bleached yet and try to do one of those set stacks, because I think maybe that would be interesting for some people. I will try to change it to a different sample.
Okay, perfect, thanks. In the meantime, we would have time to answer questions, if there are any. Or is everyone happy? So, or maybe no one of you has a microphone, so.
Maybe an additional question. So the 3D deconvolution possibility that you mentioned, is that also included in the current system?
Yeah. So the Thunder Imager actually comes with those three methods that I explained beforehand, or that I named. I didn't explain them to the very last detail. So instant computational clearing is what I showed beforehand. It's just the differentiation between in-focus signal and out-of-focus light. Then you have small volume computational clearing and large volume computational clearing. What is the difference? The difference is the order of how those methods are being combined. I showed you in the slides that computational clearing is an exclusive image improvement and deconvolution is an inclusive improvement, because it includes the photons and doesn't exclude them. And large volume computational clearing, for example, first does the exclusive improvement, meaning restricting the light that is coming from out of focus planes. Okay, and based on this data set, we are doing deconvolution. So using the reduced amount of light to calculate the photons back into the point of origin. This is, if you are used to deconvolution, is doing a lot of time improvement here.
Okay.
Small volume computational clearing is doing the opposite, or it's doing it in the other direction. So it's first doing a classic wide field deconvolution, and afterwards uses the result that you get from this deconvolution, and then applies the computational clearing as a processing cleanup filter, if you want.
And the net result is similar, or?
No, definitely not. Because if you just imagine what is happening here, it's doing the computational clearing before the deconvolution makes, in my eyes, much more sense. Wait a second, I need to comment on the specimen. Robert, I think the specimen is tilted because we only have a very thin, it's not evenly on the stage, maybe. Just maybe you want to reposition that. Okay, coming back. So from my perspective, it makes much more sense to first get rid of the light that can anyway not be nicely positioned back into its point of origin. So the calculation for this is not giving a significant difference, but makes it faster when you don't have it anymore. And then doing deconvolution. For me, this large volume computational clearing is the, let's say, most logic approach.
Okay. So you would recommend the large volume and not the small volume then? If we,
yeah, and usually I say so, yes.
Yeah, okay.
And the small volume computational clearing is in the end, in quotation marks, the classic wide field deconvolution. But keep in mind, there's a strong difference. We always also offer here the to use not only global deconvolution, but also locally adapted deconvolution. So from the Leica confocals, you know that our confocal super resolution solution is called Lightning.
Yes.
Perfect position. Thank you, Robert. And Lightning is locally adapting the deconvolution parameters depending on the signal to noise ratio in the Z stack. Okay, and this is quite a powerful improvement in the image quality and also in the deconvolution quality. But as a user, you can choose between global approach or locally adapted approach. Okay, this is just, let's say, a very broad overview of what kind of functions are possible. For this, I will go back again here to the overview. Here, if I go to large volume computational clearing, you have the computational clearing settings. And you now also see by default, we remove less light because we need the more photons we have. Yeah, deconvolution is an inclusive improvement. So it benefits from photons being around, but not the ones that we cannot separate anyway. That's why we still remove quite substantial amount of background light, but the residual light is still sufficient to do a proper 3D deconvolution. And then here are the deconvolution settings that you might know already, where again, we take for the point spread function estimation, we take here the wavelengths, peak of the emitted light, and then have here cutoff values, regularization values, and so on. So this is then for you free to choose. Usually I would really stick with auto. And what is then, of course, important for the 3D deconvolution is the mounting medium, because this shapes your point spread function. And here on top, you have the choice between adaptive deconvolution or global. So global takes one deconvolution parameter setting and applies it to the whole data set.
Okay.
And locally, or the adaptive one is the decision mask-based 3D deconvolution from Leica.
Okay, thank you.
Good. Yeah, you're welcome. All right. Somebody, I heard a ping. Patrick, can you check who is knocking on the door, please?
I did already.
Okay, thanks. All right. Good. Now we want to do a Z stack. So we have a very nice position here. Just from the single image, you see here, again, looking at signal to background. We see it's 58,000 to 3,000. This is a lot. So first thing would be to reduce the exposure time. Yeah, it's a better objective. Okay, it has a much better much better resolution and a much higher property or ability to capture light. So we can go even faster in the exposure time, maybe 70 milliseconds. 19,000 to 1,000, still 19 to 1. Go down to 50. Yeah, let's stick with that. But you see here, or maybe we do it like this, 10%, so very low input of light. 14 to 1, more than sufficient. Good. But we also check all the other properties here. Cells, okay, we see a green cell, 6,000 to 300. And this is also a very bright cell. So here we might go also lower. Because we saw, at least in the red channel, that we are bleaching sensitive. Yeah, now it's roughly 10 to 1. And DAPI actually should never be a problem. Actually, I think here we need to go lower. 10%. Yeah, still we are super high. But for now, I would keep that. Good. For you, or for us as now in the training, I will now just activate the Z-stack function, go to live, and as you know, now you set the top and bottom. Oops. So here I will go from that point, click begin, go to the other extreme, 116. Okay, this is because now I'm doing this over 100 or 25 microns, but maybe you in the future you will have a lot of those thicker samples. So here it's now 25 microns, 116 individual images. So to do now here 3D deconvolution usually also takes some time. What we do right now is I just record the stack. And as you remember, I only have active the Thunder, so the normal computational clearing mode, meaning I am only removing for each individual plane, the out of focus light. As I also explained before, the rule of thumb, the better the input, the better also the output. And what you see here is the remaining time, 15 seconds for this huge stack. Much bigger than is actually necessary. And what is being displayed is only the Thunder image. And here the third channel is now just incoming because we are here fixed at the central position. All right. And this is now here. Our magenta signal. And what we see is it's already bleached again, super sensitive. How can it be bleached when we, first of all, only had a few exposures? The point is, I bet also the other fluorophores are, or the other exposures are bleaching the RFP. So I'm drag and dropping now the M cherry to the front. And Robert, could you maybe again go to a different position, please? Okay, perfect. Yeah. Can actually see how it's still going down here. We need to further reduce the light. And I will only now set up a Z stack with going one bottom up and one down. So we could also set the settings in a way that we can always have a look here on the original stack being created. See, now it's already better, but it was bleaching while we were imaging. So it's really a sensitive sample here, the RFP. And we are quite low in our settings already, meaning we cannot go lower with the intensity. The question would be, Patrick, what is the light source that we are currently using? Is it the LED 3 or the ES6000?
No, it's LED 3, if I remember. Let me check for a second.
So this is the lowest that you can go. So here the point is to save the
LED 3.
Yeah. To save the fluorophores, you actually need to go super fast in exposure. Okay, but we can have a look now. Again, we have 116 individual slices here. We have our series, so the parent, and we have our ICC is the abbreviation for instant computational clearing. And now we will do the 3D deconvolution on top, so the large volume computational clearing. For this, you activate here the original data set and then go to the large volume computational clearing. And we need now the input in what kind of mounting medium the sample was prepared. Robert, do you know that, or should we? Yeah, you always have to unmute yourself. Yeah.
It's an immersion oil type F liquid, and the number that's on the bottle is 1.5180.
This is the refractive index of the immersion medium, but the mounting medium of the sample, do you know that?
It's glycerol based.
Yeah.
Okay. So yeah, 80-20, who knows? So I will take 80-20. There are other options. If you don't know it, you can also go to unknown or to custom. If you know it and it's not given here in the list, you can also type in the number. Okay. Let us just use here, I click on reset. and so it will only use default values, okay? Usually I use other settings, but for now we just press apply. And what you can also now see is how fast the large volume computational clearing is compared to classic deconvolution. Maybe we had the questions from the one guy who was asking the deconvolution questions. Maybe you can also judge how fast this usually takes or how long this takes if you do this big of a Z stack in order to do a deconvolution here. So what I'm using is adaptive deconvolution. That's why you can also see here the bricks, for example. And the other channels are yet not processed. So you see here processing channel 1 at 70%. And here we are roughly at the first quarter. So it will take maybe 1 or 2 minutes. But compared to a classic deconvolution, this is a drastic speed increase anyway. And you will also see that the quality is also heavily increased.
And is there a reason why you use adaptive versus global?
Yeah, I mean, we developed this because for us means Leica. It makes sense that if you have, for example, a specimen where you have uneven distributed background, this should also be reflected in the processing afterwards, right? This is the whole idea of adaptive deconvolution, that you are changing based on how is the signal to noise ratio changing in different areas of the stack.
Okay.
Yeah, that's the idea. All right. What is also possible is that, okay, of course, you sometimes don't want to sit in front of the system and wait the 2 minutes until the stack is being processed. You could also activate it during image acquisition already. But of course, the processing can only start, where is it? Here. The processing can only start once you have acquired the full volume, of course. This is something you need to keep in mind. What you could also do is acquire, I don't know, 20, 30, 50 Z stacks over the day on different positions of the slide, for example, and then mark them and put them to batch processing. This is why the batch processing here is also included. So I will show this to you in a second once it's done. Yeah, 2:44. So you could mark this and then click right mouse click and then go to send to batch processing. And then it will appear here, and here you can have your job list being created. And what you keep in mind, or what you should keep in mind, and is very important, if you find for a certain specimen sweet spot settings, yeah, like you want to image endosomes, for example, they are super small or small particles of whatever nature. They are super small, so you minimize here. Here you see also the default value is much smaller than the one with the 20x objective. And then you can maximize those settings, okay, based on the objective and use. And those settings you can also save. Here on Save Settings, you can put wherever you want to put certain settings, save them, and load them afterwards again, so that you can always have similar processing of the data sets that you are acquiring. Okay. And let me just now do another thing. I will start another processing, but in the end, we are already comparing the results. So usually I would go for a little bit more light removal. And the first ones are the actin ones. So here we go maybe down to 1000 just to see whether it's improving or not. Second channel is the green one. And then I press apply. Okay, now this calculates, and in the meantime, we are comparing the data sets. Classic instant computational clearing and large volume computational clearing. Okay. And this is now the result. Some people, so usually in this very flat sample regime, so in this monolayer cell culture, some people say that, yeah, the time it takes in order to process with the 3D deconvolution does not give me so much more improvement over the computationally cleared image. So usually they say, okay, here I can save time. But for bigger samples, of course, it can make sense to like this. Have some kind of 3D deconvolution involved. Yeah. That's actually what you see. Maybe here on top, you can see how the difference is in the processing. I don't know, I bet the resolution here on the screen or on the image that is sent actually is not as good as on the screen currently. Yeah. What is also possible is that you can always here click on a certain stack and then just click here on the 3D button, and then it's also immediately loaded into the 3D viewer, black background. Of course, yeah, you see super flat sample. But what we can nicely compare now is if we put in a second window. Then you can see what happened here, what we did to the image. Is in removing a lot of background light and then afterwards also doing deconvolution. Yeah. I think this is the point where we wrap up the session for today, I would say. I hope a lot of you learned a few things also in how to use the system, where to balance the settings that you are using, apart from just using the Thunder Imager itself or its computational clearing methods, but also hopefully you can also improve the imaging in the future.
Okay, thank you. And maybe just like to ask Robert and or Alex, who have used the system already and who found it very easy to use it, but had a little bit of trouble using the Thunder feature. I don't know if the current training solved the issues that you might have had. Alex, Robert?
Well, the only issue that I had was that I was trying to use the Thunder imaging on live images, which obviously does not work, but it did work on to process it after the image was taken. So everything seems to work as it should.
Yes, so there's not a mode, an on-the-fly mode is currently not available. This means that so that you press live and you see the image is not possible. If you activate here instant computational clearing and you start a time lapse, for example, at some point you can also go here to the open projects and click on the ICC image and not on the live image that is being displayed. And then it shows you also already the processed data sets. This is something that you can do. Other than that, of course, always when the experiment did end, you get all of the processes or all of the processed images that you set up beforehand. Yeah.
Okay, thanks.
So there are some additional questions coming in. Falco, Alexander, and somebody else is asking a question or raising his hand at least.
Yeah, I got a question. Since you already have the Zeta stack, could you generate a merge image, merging all the images you acquire instead of having the roller going one by one?
Of course, yeah.
How do you do that?
Yeah. So there are two options that are cool. So first of all, here, this one here. And so the question is, are there any other possibilities to display a Z stack other than moving around from top to bottom? Okay, yes, there are. So one is, for example, as I just showed you, a 3D image. I will reduce it to one image. Let me show that to you. Okay, do it like this. You can include a scale bar. So like this, and then you click here on Save Image. Okay, you can set up what kind of resolution it should have. Of course, this is not the stuff that you want, but it's an option. Oh, now okay, good. The other option is on processing. You have here still on the processing tools access to a bunch of things you can do. For example, projection, and this is maybe the question you were aiming at. So if you do projection, you have the option to do either maximum or maximum intensity projection or average intensity projection and so on. If you click here on apply, this is then creating a maximum projection. You also have access to this function just on the display on the screen. If you click here on this max button, then it's doing maximum projection. There's also another option that I think doesn't work so nicely for those cells, but we will try this. And this is the so-called extended depth of focus. So a multi-focus image where several layers of focus are overlaid in each other. Okay, so what is happening here is that if you have now a Z stack, right? And if you move to the Z stack, each image or each structure has a certain part in focus or not in focus. And the image contains of 2000 by 2000 pixels. And for each pixel position, for each channel, within the Z stack, there's this one pixel looked for that has the highest contrast compared to the neighbors. And this is then exported to the final EDOF image, so extended depth of field image. This is how a multi-focus image is being created. And this is this can create a nice, or it will always flatten, of course, the 3D information into a single layer. Depending on the structures in the image, it makes sense sometimes, but it can also make absolutely no sense. I will also do the calculation here right now. EDOF, apply, and we let it calculate. So what is also nice in general with the Leica software is that you always create, if you do a certain processing, doesn't matter whether it's computational clearing or whether it's maximum projection, you are always creating an offspring of the raw file. Okay, you're not overwriting your raw data. Okay, and then we can find here also the image here. This was the processed image that we created first. This is now a single image from the Z stack. This is the processed image. Okay, the maximum projected image. And then there should also be a folder with multi-focus, scan one. And as I said, this makes no sense at all. Yeah. Okay, here the processing, I don't know whether I checked the wrong processing, but yeah.
So one small comment from my side: color cameras are more suitable for extended.
Yeah, that's the way usually where you do this. Yeah. But maybe this is the better reference channel, but Yeah, we receive. So here, usually go for maximum projection. This is the classic way of presenting Z-stacks. Yeah. Is that answering the question?
Yeah. That's actually how we do it in the confocal, so should be familiar.
Yeah, it's a similar function, actually. Okay. There were, I think, also other raised hands.
Yes, sorry, just two short questions. So the first one is it cannot be used for live cell imaging.
What cannot use for live cell imaging?
It's only for the, it's not inverted. It's only for fixed cells, not live cells.
No, that's not right. You can do you can have computational clearing for every data set that you record.
This is an inverted microscope, Jason. It's just that we don't have a chamber for CO2 and temperature incubation.
Okay, so it's just like normal confocal microscope. Yeah.
That's true.
Okay, and the second one is, do we have an option for additional channel? Because sometimes we have to do multiple staining, not more than triple, or even 4 or 5.
Yeah, this is a question not for me actually, because currently as the setup of the microscope is, there are 3 colors possible, but of course you could also get more cubes if you want. But this is nothing that we can, I mean, this would need to be purchased.
Okay, yeah. That's
so please stay in touch with me or with Professor Favril for this.
Yeah, maybe just coming back to this processing again. So this one here was the maximum intensity projection. And now if we have a better reference channel, so I use now the DAPI channel for the extended depth of focus. And then this is what we create. So here, I think it's even better than the maximum projection. But of course, you are superimposing layers of focus that were never in focus. So yeah, this one has to keep in mind. Just now, quick. Wrong button and zack. Yeah, so left-hand side is the maximum intensity projection. Sorry, the extended depth of field. Yeah. Okay. Further questions? If not, I would say, first of all, thank you. Also for being such in a transformative mood to also do a training now remotely. This was actually quite nice. Of course, this was only the first part of a training, so you will see one of the application specialists soon on your place once we can travel and access buildings freely again, and we can have a lot of people around. So, but I think to get you all started and able to work, I think this was a very nice training, at least from my side. It was a lot of fun. Nice samples. Thank you, Robert, again for setting up everything.
Yeah, I actually didn't make the samples. Cliff made the samples, so I just came to sit here.
Yeah, but you were the assistant that was needed, because I cannot apply oil on the objective remotely yet.
So one comment from my side, please stay in touch with Professor Favril and myself so we can plan further actions when needed. Obviously, in this case, it's nice to have some use with the microscope and get together, gathering all the information and questions you have to plan a second step on site when possible.
Okay, thank you to you both, especially to Falco for the excellent training. I think this should be sufficient to get us started. And indeed, we can then see what kind of questions, if any, pop up during the use, and then we can get back in touch with you.
Yeah, exactly.
Happy
Perfect.
to. I will share the recorded session with you, Herman, as soon as possible.
Yeah, that's excellent. Thank you.
Yeah,
Okay.
stay in touch. Thank you, Falk.
Yeah.
Have a nice day. Bye-bye.
Bye-bye.
Thank you.
Thank you, Paco.